As we continue to look at momentum, the next thing we're going to do is have a little bit more of a look at collisions. As we saw in the last video, all collisions are going to involve conservation of momentum. Explosions likewise involve conservation of momentum as well. So basically, as we stated in the last video, the total momentum before a collision or an explosion will be equal to the total momentum after that collision or explosion. So that's the other way to think of it, to make it a bit easier to process. And I'll just rewrite it here just as a reference. So we had that equation m1u1 plus m2u2 is equal to m1v1 plus m2v2. So in the case of a collision, as we've seen in class, we can have a number of different scenarios involving this initial condition. So whether the masses are the same or different, whether the initial velocities are the same, if one of them is zero, if the initial velocities are in the same direction or in opposite direction. So there's lots of different scenarios. So I'm not going to bother going into those specifically, but I do want to go into two different types of collisions that are important to identify. And two different classifications that we're going to use. And the first one is that a collision can be elastic. And what we mean by elastic is that in order to identify whether a collision is elastic or not, you need to look at kinetic energy. So for an elastic collision, kinetic energy is also conserved. So what we mean by that, similar to this equation that we've got for conservation of momentum, we can go through the whole derivation, but I'll just write the final equation. So basically we'd look at the fact that the initial kinetic energy of object 1, so that's half mu1 squared, plus the initial kinetic energy of the other object, m2, sorry for the m1, m2u2 squared, is going to be equal to the final kinetic energy of both of those objects. So half m1v1 squared plus half m2v2 squared. Now notice here I'm not using the vector notation for the initial and final velocities. Hopefully you can remember that kinetic energy is a scalar quantity, not a vector quantity. So there's a key difference between the two equations there. For momentum we're looking at the vector properties, but for kinetic energy we're only looking at the scalar quantity. So another way to think about this scenario, I'll just want to make this note as well. If we're saying that that kinetic energy is conserved, another way to think of that is that there are no energy losses to other forms. So all of the kinetic energy that we have to begin with is the same as the total amount of kinetic energy that we have after. So that's elastic collisions. The other type of collision that we need to be aware of is inelastic collisions. So the prefix in here basically means sort of the opposite. So in this case, kinetic energy is not conserved. And that means then that we can't use this equation up here because we don't have any wasted forms of energy in that equation. You could possibly add some sort of energy losses over here, but that would require actually knowing how much energy is being lost to those forms, and you won't usually be able to determine that very easily. When we say that kinetic energy is not conserved, what we're really saying is that some kinetic energy is converted to other forms. And those other forms are fairly common. You will have seen them before as wasted forms of energy. And that conversion is happening during the collision. And the forms that you usually see when you're dealing with an inelastic collision would be things like sound and heat. Now there are a few different types of inelastic collision that we need to be aware of, and a lot of resources sort of can lead you a little bit astray, given that there are a few different ways that these inelastic collisions can occur. So the first one is if the objects stick together. So in that case, we're definitely going to have an inelastic collision, given that as they stick together, the kinetic energy is being converted to other forms. So there's the first one. But you also need to be aware that objects can bounce apart. So if objects bounce apart, that could be an inelastic collision, but we'd need to analyse the kinetic energy in order to determine whether or not it is inelastic or elastic. Now, if we're dealing with elastic collisions, then we can't have objects sticking together at all. The objects will definitely bounce apart. But like I say, in order to determine whether it is elastic or inelastic, you have to identify whether kinetic energy has been conserved or if it has not been conserved. Finally, the last thing in this video that we'll talk about is an explosion. So with an explosion, if you think about it, the initial kinetic energy, usually, if you've got, say, a bomb sitting stationary or something that is combustible and is about to explode, the object is usually going to be sitting there stationary. So there's going to be no kinetic energy to begin with. After it explodes, then parts are going to be moving in all sorts of different directions. So the kinetic energy is going to now be kinetic energy. So it's fairly obvious just by thinking about those simple scenarios, kinetic energy is not conserved in an explosion. Now you might think of a situation where if you've got, say, you throw a hand grenade and as it's moving through the air it explodes. Yes, there is some initial kinetic energy of the hand grenade as it's moving, but the final kinetic energy won't necessarily be the same as the initial kinetic energy. So a way to think about that is, again, I'll just make a note here. If an object is initially stationary, then what we can say is that the momentum is equal to 0, and the kinetic energy will also be equal to 0. After the explosion, we know that the total the total momentum, I might just put a T here to indicate total, the total momentum will still be 0 kilogram meters per second. If there are only two parts that the object has exploded into, then the two parts will have equal and opposite momentum. So let's say we've got say a bomb initially that's going to explode, and then as it explodes we get one part that starts moving off this way and another part that starts moving off that way. Then mass 1 and velocity 1 and mass 2 velocity 2, the product m1v1 will be equal to the product of m2v2 but negative. So the total momentum in the end will still be 0 kilogram meters per second. The initial kinetic energy, however, is going to be greater than 0 because we now have motion of these two parts, and so the object or the kinetic energy of each of those parts will be greater than 0. So add those two together and we'll have a non-zero kinetic energy. So you can see there that with an explosion, momentum is still conserved, but the kinetic energy is not. The other reason for that, if you think about it, with the momentum, we've got the vector quantities, so the momentum of each of these parts will be in opposite directions, whereas kinetic energy, it's a scalar, so the direction's no longer important. So we're just looking at the total, and as a result, the kinetic energy is obviously going to be greater than zero. We'll have a look at a few questions in class that deal with these sorts of ideas. Might even dig up a few past exam questions so that you've got a better sense of the sorts of things that you might need to be able to answer under exam conditions.